All right. So thank you very much. I would like to thank the organizers for this very exciting conference and for this opportunity to speak. I'm very thankful. And so as we've heard, my name is Emmanuel Schaan. I'm a grad student in Princeton University. And I'll be presenting work done with Simone Ferraro, who's now a postdoc in Berkeley, Mariana Vargas Magana in Mexico, Shirley Ho, who will be here soon, Kendrick, and the Apple collaboration, including my advisor, David Spergel. So we heard in the introduction that a good part of the information content of the primary fluctuations of the CMB have been extracted, but there's still a lot of information in the CMB about the large-scale structure because the CMB acts as a backlight and it illuminates the large-scale structure, and for this reason, many properties of the large-scale structure get imprinted on the CMB. So the ones I'm going to be focusing on here is the peculiar velocities or the momentum field, because the conference is about cosmic flows, and this is what I'm working on. So in terms of peculiar velocities, from the point of view of an observer, you have line-of-sight velocity and velocities across the line of sight. So for the former, this would be the kinematic Sunyaev-Zeldovich effect, the Kse effect, and this is what I will be mostly focusing on. And then for the purpose of perhaps discussion, I'll just mention and say a few things about velocities across the line of sight, and that would be the moving lens halo effect. So these are the things we hope to learn by measuring the kinematic Sunyaev-Zeldovich effect. As I will explain shortly, the KSZ couples baryon physics and peculiar velocities. So depending on your point of view, it's either a good or bad thing. It's a good thing because there's more information in it. It just makes it harder to untangle the both. But basically from the peculiar velocities, of course, from their amplitude, what you hope to learn is the growth rate of structure, this little f right here. That you measure in redshift space distortion. And this is an important quantity to measure because it can help you constrain general relativity or modifications to it. Another good thing about the kinematic Sunyaev-Zeldovich effect is that even if you don't detect it, you actually learn something. And that's the Planck paper on constraints on peculiar velocities. By not finding a bulk flow, this is enough to rule out some void models as alternatives to lambda CDM. So I think that's very interesting. And finally, velocities are just another independent measurements of the same initial conditions. And so in particular, if you worry about the large-scale power deficit that you see in the CMB temperature power spectrum, and if you're wondering if this is a fluke or not, it might be useful to look at it in velocities also because the power spectrum of velocities peaks on larger scales. So in principle, you might have larger signal-to-noise there. The second aspect of the kinematic Sunyaev-Zeldovich effect, and this is probably the one I'll be focusing on the most, is that it teaches us about baryon physics. And the questions we're trying to answer here is basically this missing baryon problem, which is the fact that the baryon abundance in the universe is very well constrained from deuterium abundance, so Big Bang nucleosynthesis, CMB observations. And this seems to agree with what is found in Lyman alpha observations. However, it turns out that at redshift 0 in observations of clusters in X-ray and thermal Sunyaev-Zeldovich, only a small fraction of these baryons are found. So it would be nice to actually see where they are. And that answers also the question in which phase are these baryons and what are the profiles inside the clusters. And that would be interesting to constrain because it would be a constraint on models of cluster physics and the processes that inject energy inside clusters. So these are the things we're trying to learn about, but what is the Kse effect? It's basically the change in energy of CMB photons as they bounce off moving galaxy clusters. So it's really just Doppler effect bouncing off a moving mirror. And because it is a Doppler shift, it's proportional to V over C. And it also depends on how good of a mirror your galaxy cluster is. And that would be this Thomson scattering optical depth, which depends on the line of sight integral of the number density of electrons times the Thomson cross-section. So right away, a good property of this KSZ effect is the fact that it's linear in electron density. And that should be contrasted with X-ray observations that basically come from Bremsstrahlung. So that would be density squared and some square root of temperature. and also thermal Sunyaev-Zeldovich, for which what matters is the pressure profile, so density times temperature. So in both cases, you have something that's really sensitive to the densest, hottest part of the cluster. So that would be the center, and perhaps a little less well-suited to see the baryons on the outskirts around virial radius of your cluster. So that's a good thing about the Kse effect. Another property is that since it's a Doppler shift, it preserves the blackbody spectrum. What that means is that you can't just extract it from the CMB by doing frequency cleaning. However, the people who did frequency cleaning to extract the CMB also extracted for us the Kse for free. And finally, I should point out that it is a very small effect if you compare it to the CMB primary fluctuations. And of course, that's a bad thing, but it also means that the Kse effect is actually a very good thing to be looking at right now, because we're in the regime where CMB experiments allow to detect it, and I will show that right away. But before that, I just wanted to point out that to detect this Kse effect, you cannot just stack clusters like you would do for the thermal Sunyaev-Zeldovich effect, and that's because the sign of the effect changes with the line of sight velocity, and so on average, you expect a cancellation. So in practice, what we're going to be doing is we're going to stack weighted by an estimate of this velocity, and I'll explain where this estimate comes from. But this is why current and upcoming CMB experiments are going to make this Kse effect really, really exciting. So this is a power spectrum of a few things that are on the sky, and I added some curves for typical detector noise. So that would be relevant for current ACTPol, and that would be for a futuristic CMB stage 4 experiment. So what you can see is that this Kse curve is the red curve at the bottom, and it peaks on very, very high multiples, very small scales. And so if you want to see the signal, it matters that you have a high resolution. And to give you an idea, this would be a beam relevant for ACTPol and again, CMB stage 4. And because the signal is so low compared to the foregrounds, for which main foregrounds are primary CMB, this blue curve, and detector noise, it matters to have high sensitivity, low noise experiments. And that's basically what we're getting. So what that means is that in the future, there's even hope for detecting the Kse directly at the level of the power spectrum in maps that have been cleaned for foregrounds. But right now, this is not what we're doing. I should also point out that this Kse signal has contribution from both reionization and late time. And the reionization signal is certainly very interesting because it contains information on the topology and the patchiness of reionization. And that's kind of the grail of Kse. But for this talk, I'll be focusing on the late time ones, the one that's due to cluster. And so if you're interested in these free electrons around clusters, you might wonder which cluster sizes you should be looking at and up to which redshift. And this is what this plot is trying to answer. This is just a very quick, simple signal-to-noise estimate saying that the number of electrons scales with mass, and that your signal-to-noise, if you're going to stack, scales the square root of the number of objects. And for this, you just take a mass function and the cosmological volume out to a given redshift. Mass of the halo, or? Right. And you can see that where the signal is dominant is for these intermediate mass galaxy groups and down to about redshift of 2. And so this signal from galaxy clusters has been detected in the past. So these are the previous detections of the Kse effect. The first one by Nick Han and the ACTPol collaboration, uses this method of pairwise velocities. So again, trying to cure the fact that if you just stack your clusters, your signal cancel. What you do is that on average, if you have 2 galaxies, their mean relative velocity will be towards each other. So that if you take pairs of galaxies and measure the temperature around these galaxies and subtract them, you have an estimator for this mean velocity, which is on average 0 and dependent on the separation. And so this provided the first detection of the Kse effect. And so it's a statistical detection. There has been also an individual detection on a very particular object with a very high mass and very high velocities of the components. This is about 10 times what you would expect from the cosmological RMS velocity, but this is because it's due to a merger. So with good frequencies, you can see it on this object. Turns out there aren't so many objects like this one on the sky that are available, but so it's nice. And this paper, finally, that was published recently by the Planck collaboration, pretty much uses the same method that we are using, and it's based on reconstructed velocities. So I'm going to explain this method. And in order to do this, I will first take a small detour and say a few general things about peculiar velocities. So peculiar velocities, the ones I'm talking about right now are not due to initial conditions, they're due to the gravitational instability. And what I call peculiar velocity is really just the normal velocity, which is physical displacement over cosmic time, to which you subtract the Hubble expansion. So you take the motion of the galaxy, you subtract the Hubble expansion, and you get this co-moving displacement per unit conformal time. And it turns out, because there is a mass conservation, in the linear approximation, the velocity field is entirely constrained once you know the density field. And the relationship between the two is some sort of gradient and the linear growth factor here. And intuitively, what this equation means is really, really simple, and it's illustrated here. And so this is an n-body simulation, and it really just says that the reason why you have more masses in here is because the mass has been moving towards it. So intuitively, this is really simple. In linear theory, this velocity field also is a perfect gradient, and that will matter both for the properties of the scale dependence of this field and the reconstruction method. And finally, maybe a side comment. If you were to have access to both velocity and density field on the same patch of the sky somehow, then you would be able to measure this growth factor f without any cosmic variance. So it's just a neat thing to think about. But more properties of these peculiar velocities. The time dependence determined by this a times h times f times the growth factor during matter domination is basically as square root of a. And after matter dark energy equality, the velocities slightly decay, but are basically constant up to redshift 0.5 or so. And the typical number to have in mind for the velocities that we're going to be talking about is about 300 kilometers per second. So p over c of 10 to the minus 3. Last thing about peculiar velocities, I wanted to illustrate why there is this anisotropic scale dependence of the velocity field. And the idea here is basically just that since your velocity field is a perfect gradient, what that means, if you think of it in Fourier space, is that the direction of the velocity is parallel to the wave vector, which means your velocity component mostly varies on its own direction. So if you're looking at the line of sight velocity, the line of sight velocity is mostly varying along the line of sight and not so much across the line of sight. And this is something you can see. This is velocity reconstruction done on mock data for the CMAS galaxy sample. And color-coded here is the line of sight velocity. So just to orient yourself, the observer would be somewhere down here. And the galaxies have been put in a 3D box. And surfaces of a constant redshift are these arcs. And you can see that the blobs of constant velocities are both very large, over hundreds of megaparsec, which illustrate again this thing that velocities have power on larger scales than densities do. And you can see that these blobs are also very anisotropic, and they're much more squashed along line of sight, again, because this field is a perfect gradient. So onto the velocity reconstruction. What we do, and this is done by Kendrick here and Mariana Vargas Magana in Mexico and Shirley Ho from the BOSS team, is to take these CMAS galaxies, and since you have redshifts for them, you can put them in a 3D box. And once you've done this, you can basically take this gradient modulo a bias and get your velocity estimate. And that involves getting the density field, which of course means you need a bias, but you also need either a smoothing scale or and that's the method that Kendrick is developing, some linear filtering. So basically, this is what you get, and you see these very large patches extending along the line of sight.
So, question: do you do anything with that fingers of art?
No, this is really only the linear velocity field. So we take into account the redshift space distortion, the linear part, the Kaiser part, but no redshift, no fingers of God.
So you tested like any nonlinear effects?
So it turns out testing this velocity reconstruction against MUX, for which n-body MUX, for which you know the true velocities, has been done by Kendrick and Mariana.
Okay.
And for our purposes, for the analysis, what matters to us is basically what is the correlation coefficient object per object between true and estimated velocity.
Right.
And so that's something we can calibrate from MUX.
And what is it? What is the
calibration?
70%
70% is the typical number.
Is that R or the R squared?
Oh, that's R.
So does that mean reconstructed velocities are 70% smaller than, or 70% of the actual velocity?
I really mean yes, V true, V rec over the right.
Yeah.
Sorry. But yeah, definitely it's useful to have better velocity estimates because our signal to noise scales directly proportional to this correlation coefficient.
Okay, 70% sounds like a huge.
Right.
It's a 30%.
What is the redshift range that the reconstruction is?
So this one, since it's the CMAS galaxies, it's between 0.4 and 0.7, and the median is about 0.57. So these are the data sets we're using, and as I said, we're going to stack clusters weighted by a velocity estimate. So the temperature data for these clusters comes from ActPol, and we have a map at a single frequency with these properties, and we're going to do aperture photometry at the position of each cluster. I'll say a little bit more about this. And our cluster sample is actually made of the CMAS galaxies, and the idea here is that a high fraction of these CMAS galaxies are actually at the center of galaxy groups of typically 10 to the 13 solar mass. And this comes from various sources that I can say a bit more about. And so on this galaxy sample, Kendrick, Mariana, and Shirley have given us reconstructed velocities, and we will use them. So for each object, we have a temperature measure from aperture photometry, and an estimate of this optical depth, which is basically proportional to the mass of the object, and the reconstructed velocities. And what we want to know is if delta t is equal to tau times v. So let me just say a bit more about delta t, and then show what we expect to see before showing what we actually see. By aperture photometry, what we mean is that we're averaging the CMB temperature on a disk of a certain size, and we're subtracting the CMB temperature on an annulus of another size around it. And the idea behind this is that, so our foregrounds are noise and CMB, and the CMB mostly varies on degree scales. And so if your disk is of order arc-minute size, the CMB won't vary much between the annulus and the ring, and so you cancel out a good part of the CMB. And of course, that statement will depend on the size of your filter. And that's what's shown here. So here, theta disk is the radius of this disk in arc minutes, and you can see the two main components to our source of noise, CMB and detector noise. And so as the disk goes to 0, the noise from CMB goes to 0 because the CMB doesn't vary on such small scales. And you can see that the typical noise from the CMB is much smaller than the 110 microkelvin you would get if you were just averaging over a disk. And what you can also see is that because there's noise, there's an optimum for the disk size you would like to choose. But anyway, we couldn't go much smaller because of the beam. And we're faced with a bit of a trade-off. And the trade-off here is that if you want to encompass all of the free electrons around your clusters, you want as big an aperture as possible. But at the same time, if you want the smallest possible noise, you want the smallest possible aperture. So in terms of signal to noise, there's actually an optimum somewhere in the middle. So this is the aperture photometry we do. And this is just some very simple expectations for what you would hope to see. So here we've defined this number alpha, to which we intentionally didn't give a physical name, because to go from this to actual number of electrons, there are a few steps that I will talk about. But basically, alpha in this equation means that if you find it consistent with 0, it means you detected no KSZ. And if you find it consistent with 1, we normalized it to mean that the baryon abundance inside your clusters follows the cosmological abundance. And this is just trying to show you the type of curve you expect to see as a function of the aperture. So obviously, when the aperture increases and increases, you expect to see more and more of the electrons around your profile, up to some point where you asymptote. And the curve goes up if you have more electrons, and the curve slides to the right if the size of your cluster changes. So these are just very obvious things that will just help understand the next plot. So in principle, these two things should be non-degenerate. You just look at the asymptote and you see how many electrons are there, and then you look at the curve here and you know the size of the cluster. However, like I showed before, the uncertainty on your data points as the disk increases in size will blow up, which means that there isn't a clear asymptote for us. And so at this point, there's a pretty good degeneracy between these two things.
Is the velocity field coherent across this 8 arc minutes?
Oh yeah. So the typical at redshift 0.57, these 2 arc minutes or so would be basically the viral radius of this 10 to the 10 solar mass group. So it would be of order of megaparsec or so. And these velocities are coherent on hundreds of megaparsec. So on the next plot, I'm going to show this and the data on it, and just to warn you, this axis will be divided by this one squared, just so that the points are visible. Sorry?
I guess I missed. What are the different curves?
Oh, right. So here, the different curves are what you would obtain if you increase the total number of electrons associated with each cluster.
Oh, right.
And these ones are what you get if you increase the size of
So
the.
this is theoretical expectation.
Right. And there's a lot of uncertainty on this, so this is kind of at the cartoon level, just to guide the eye. So these are the results we find, and this red wide band is supposed to be the same as the previous ones, and showing some uncertainty on both the size and the amplitude, just to guide the eye. And so for now, it looks like a 4 sigma rejection of the no KSZ hypothesis. So that's looking encouraging, and we expect the signal to noise here to be multiplied by probably 2 within the next year as the area of the CMB maps that we have increase. But
points are, I guess, are not independent of each other?
they are very, very correlated because they're aperture photometry on the same objects, just larger.
But none of them look like 4 sigma. But you're saying somehow the combined thing is 4 sigma?
Right. So we have covariance matrices, and that's the signal to noise that comes out.
Sorry, you keep getting more and more electrons as you go out. There's no boundary to the object, so alpha should just keep going up, right? It shouldn't saturate.
Right. You can. So actually, this is related to this 2 halo term here. But otherwise, you would expect if the electrons around you are not associated with your group, you might expect at some point that the velocities become uncorrelated, and then it just becomes a source of noise, but not signal. However, you're right that that there is such a 2 halo term. So these are the various systematics that one has to characterize before being able to go from a detection to actually counting the number of electrons. And I think this is basically the specificity of our project, is that we're trying to explore these systematics really carefully. So I have pretty much ranked them from harmless to the most harmful at the bottom. So I can say more about this. I have more slides, but maybe in the interest of time, I won't spend too much time. There's definitely something very interesting happening with the 2 halo term and the scattering mass. So if you're interested, you can ask me. So this is not the end of the talk. This is the end of the KSZ part. Maybe I shouldn't have said that and try to get a free clap, but someone did that in the conference in Munich, and I found that was a good idea. But so basically, within the next year or so, we expect to be able to start giving numbers for the baryon abundance in these galaxy groups and the size of the gas profile in these galaxy groups. And in the next few years or so, the signal to noise should really, really soar. So S-O-R-E, S-O-A-R. And that's due to two things. I guess in the shorter term, it's just the increase in area of the CMB maps that we have. For now, this detection is only 600 square degrees. And there are several funded experiments that will go to the same depth and with the same resolution to half of the sky, something like Advanced ACTPOL, which should start next year. And in the longer term, this CMB stage 4 experiment, which is still futuristic for now. So right now, basically, because of our small map area, we use a very small fraction of the CMAS galaxies. But in the future, we'll be able to use all of them and use data from these upcoming spectroscopic surveys. So basically, in the next few years, we should have a factor of 10 increase in signal to noise from this method. And that becomes really interesting because then you can start not only constraining two numbers, but actually a gas profile, and you can start binning your measurement in galaxy type or galaxy mass and start to learn very interesting things. So that's it for the kinematic Sunyaev-Zeldovich effect. And then I will just say a few things about velocities across the line of sight. So this is much less mature. My talk on it is much less mature, but hopefully it will still be interesting. So this effect has been described a lot in the literature, and I'm going to just give a small pedagogical explanation for how things work. So here I'm just showing photons coming from the CMB and going towards the observer, going through a gravitational potential. So of course, what happens if the potential is static is that as the electrons fall down the potential, they gain energy. And as they exit the potential, they lose that energy, and so there's no net change. But in the moving lens effect, what happens is that as the electrons fall down the potential well itself has moved, and therefore on the way out, for this photon, for example, you have to escape a shallower potential well than you fell into, and the opposite is true for that photon. So in principle, you hope to see this kind of dipole pattern, where on the trailing side of the cluster, there's an increase of energy and a decrease of energy on the other side. So yeah, this is the kind of ISW-like explanation of the effect. This is just showing you what this should look like for an SW halo of 10 to the 13th solar mass with this kind of typical velocity and redshift. And that's the dipole pattern you see. On top, I just wrote the ISW interpretation of this pattern and how you can write it in terms of the velocity across the line of sight and basically the lensing deflection. So what that suggests is that this effect can be interpreted as a lensing of the dipole due to the motion, the dipole that the cluster sees due to its own motion. But turns out there are also other dipoles in the CMB, just normal CMB gradients, and that's a source of confusion. So basically, when a cluster produces lensing on the CMB, the cluster lenses the CMB gradient it sees, and this effect has exactly the same pattern, but 50 times larger. The good thing, though, is that the directions should be uncorrelated. So if you have information on the velocities across the line of sight, you might be able to extract this one. And the cluster lensing effect is detected. So I just thought this is definitely not at the level of the kinematic Sunyaev-Zeldovich effect in terms of what we can learn from it. But I just thought it was a cute effect, and I should point it out. And maybe just out of curiosity, this is a very quick forecast from what we could get from it. And from current data, this is the typical upper bound you could place on velocities across the line of sight. And with futuristic CMB experiments, stage 4, and new spectroscopic data, you could actually get a detection of this effect. You could also try to get constraints on the universe rotation. These won't be competitive with the ones from the Planck quadrupole. but still it's interesting. And I guess this effect does not depend on baryon physics, contrary to the Kse. So that's it for the moving lens effect. Here's my conclusion. Mostly, I wanted to say that the Kse is a powerful probe of baryons physics. And perhaps once this is understood, there's hope to get at the velocities from this Kse. I think it's also a very good time to be interested in it because the signal to noise are going to increase a lot. So I think we can learn a lot from it. Yeah, that's basically it. Thank you.
Wonderful. Thanks, Emmanuel. Do you have plenty of time for questions?
Yeah. So this moving lens effect is of order phi times v,
Mm-hmm.
right? And so phi to 10 minus 5 and v to 10 minus 3.
Right.
So it's like 10 minus 8 of the CMB temperature?
Oops. Sorry, let me.
0.01 microkelvin in that diagram. Oh, okay, good.
Right.
Okay.
All right. I guess my computer doesn't want me to talk anymore, but
So you got it.
right. So yeah, a 0.02 micro K would be the order of magnitude for a 10 to the 13 cluster, and that is 50 times smaller than cluster lensing dipole, which has the same exact pattern. This one is currently detected at a few sigma level, so this one won't be right now. That's this quick forecast here, where you can only place an upper bound, and you see this is 20 times the cosmological value. Yes.
What is universe rotation?
Oh, it turns out that's something you can read about in these Planck papers, but there are these Bianchi models of the universe.
So like Bianchi 7.
That's right.
So you're saying the limit from this is not as interesting as the one that's already in.
Right. And by a lot.
By 5 orders of magnitude.
Right.
Was there a reason that was thought to be interesting for that?
I guess the idea here is if with current data, if you can't detect the effect, you can place an upper bound on it.
So I have a question. So I guess you mentioned the cross correlation coefficient for this reconstructed versus the actual velocity from simulation. But I guess what I was wondering was, is there a bias in reconstructing velocity?
So I think the corollary, in particular with these Wiener filtering methods, is that you get a multiplicative bias associated with your correlation coefficient.
And what is that?
So I think it's
something, but you calibrate it.
The ratio is in. So I think if your correlation coefficient is 70%, so your correlation coefficient is 30% low, your reconstructed velocities will have to be 30% high. Is that correct? But again, that's something we calibrate from simulation.
I was thinking about it, but it's not quite clear because the correlation coefficient just tells you how correlated these things are with each other. But whether there's a multiplicative number, that's just something that the correlation coefficient doesn't tell you. No,
that's right. That's completely right. So in terms, if you want to get this number alpha unbiased, you need to know both the correlation coefficient, which decreases your correlation, and this multiplicative bias. And this we do with these mocks.
Right.
In terms of signal to noise, though, only the correlation coefficient matters, it turns out.
Okay. So, but then I guess the fact that there is a multiplicative bias, it's something that's not expected from linear theory. It should be one if linear theory was correct. So I'm just wondering what that multiplicative bias depends on.
I think it might also be in part just due to the fact that there are nonlinear effects on the velocities that you're not taking into account.
But nonlinear effects wouldn't give you because it doesn't violate the equivalence principle. So everything would still move together even if they're nonlinear. So a nonlinear effect just gives you a random noise, which tells you because there is no exact correlation. But on average, things still follow each other.
I have to say that, Wiener filtering generally is biased low by construction. That is the estimator that minimizes the residual dispersion.
Okay, and
if you want to get rid of it, you just
okay. And I guess this disk radius, is this something that I would think if you want to have an optimal estimator, you don't even have to assume a disk radius.
That's right. If my computer cooperated, I could show you. So there's this method of using matched filtering instead of these aperture photometry. And so, of course, in terms of signal to noise, these are better. The issue, though, is that when you do matched filter, so you have a filter of which the profile is determined by the profile of your cluster, which you have assumed, and the noise. And it ends up being slightly sensitive to your assumptions on the cluster profile,
okay, so
as well as miscentering.
Then, since you don't actually know what the cluster profile is, you don't know exactly what the
that's a bit the same thing as is used when people measure thermal Sunyaev-Zeldovich, where they use match filtering for the purpose of detection, but for the measurement, they still stick to aperture photometry.
So I guess ideally you want to fit for both of them, not just an amplitude and a shape.
Right.
You may not be able to measure it very well. But
That's right.
Other questions for Emmanuel? If not, let's thank him again.
Thank you.